Okay, welcome back, everybody. I want to go into another lecture regarding chaos and fractal dynamic systems. And today, what I want to build upon is what we have been discussing so far. And this is using the Colpitts oscillator kind of as a foundation, backdrop, whatever you may call it. I want to now talk about symbolic dynamics. What is that? How can you use it? How can it be beneficial in studying chaos or even utilizing it or applying it to useful situations? We'll just start to delve into this. Now, as you know, we've talked about the background of chaos. We've talked about its characteristics, the butterfly effect. We've introduced the notion of the Poincare surface, and as well as some concepts of synchronization, which we talked about last time, and even controlling chaos. And now we're talking about symbolic dynamics. And then if we have time, we'll go through and apply that, because synchrodon amplification takes the control of symbolic dynamics and symbolic dynamics, controlling chaos and synchronization, of course using a Poincare surface, as all of this combined. And of course, the sensitivity to small changes allows you to do the control using very little energy, and therefore that's where this amplification comes from. So this synchrodon amplification takes all of these points into account. If we have time, I'll go into ways I've used it for image processing, but something tells me we won't make it. But anyway, let's get into this. So here's the attractor that essentially has been integrated forward several hundreds of thousands, if not a million times, I think. And if you think about it, you have this, it's moving around in this direction, and it, cuts through this surface. And so you kind of know that, right? And it continues to move around and do that and so on, right? And it cuts through the surface. Now, so we've erected this Poincare surface here, and I want to just make sure I continue to use the terminology so that you can use it conversationally and get comfortable with it. But this is the Poincare surface erected in a constant plane of I sub L. Probably right around here is where it sits in a constant I sub L, and every time it cuts through it, you take a point. Well, if you do that constantly, you get something that looks like this. These are the several, I'm going to say is about 50,000 surface crossings that make up this Poincare surface of section right here. As you can see, there's V sub B and V sub C, and that's the arc that you see. So this attractor is thin, almost like a thin slice of pizza dough. You could almost think of it like that. That you're moving around in, state space, but it's really every time the trajectory passes through. But you kind of can look at the attractor almost again like this flat sheet that is kind of warped a bit, but lying in this state space. Now, and also, if you remember, we created these return maps, which basically says that when this point passes through in the collector voltage here, what is the next point that's going to cross? What would that look like? And that's where you get these return shapes. This is for the collector and for the emitter, which are, again, are the two values on this Poincare surface arc. Interestingly enough, it has a one-dimensional map type of flavor to it, meaning it's just a single arc with the odd shape, but it's still got a single arc. So what if we did this? What if we said that, start off just somewhere in the middle, we were going to draw a line. And remember that these are points that are falling through here. So if I said that any point that crosses and falls on this side, I'm going to give it a 0. And any point that crosses and falls on this side, I give it a 1. Okay?
Sorry.
No, that's fine.
My grandson, this is my favorite room.
Well, hi there. How you doing?
Say hi.
Got a guest here. I'm recording, but it's okay. I got a guest that's popped in, so I'm talking about chaos theory and all that stuff. Take it easy. All right, just a little guest that popped in. But anyway, so if I apply 0 here, 1 here, then every time this passes through, this will generate a sequence of 1s and 0s. Okay? So you have to believe that. All right, now, and you could look at it again. Let's go back to the Poincare surface, and if then I selected about 10.4, so a straight line through there would generate something like that. I didn't draw the line very well, but you'll see that VE has a value that's associated as well. And let's just say that, okay, it's 10.4 is about here in the middle, and as you can see here in the middle is about, minus 0.23 or something like that. No, or no, 0. No, where's the middle? It's more like this. So it's a negative number, but you'll see that more right here. It's if I drew this line straight, let me get rid of this line. If I drew that more straight, it's some negative number right there. Okay? But that's the partition. So this is called the generating partition. And now you're free to put this where you want, but what you would really want is the probability that a point would fall on this side as much as it will fall on the other side, a 0 or the 1 side. So then you would have a higher chance of generating more of the bits that you want. Okay, now we're going to do a quick refresher in binary. Okay, so our system of using numbers is in the decimals, right? So that means we have 10 digits. 0, 1, 2, 3, 4, 5, 6, 7. All right, how did I not make that fit? Let me try it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's our decimal system. And we take those digits and we put them in such a thing where we have something to the 0s place, to the 1s place. No, sorry. Hold on. is 10 to the 0, 10 to the 1, 10 to the 2, so on, right? So I'll take a number like 8,642. Okay? That means that is 2 times 10 to the 0 plus 4 times 10 to the first plus 6 times 10 to the second plus 8 times 10 to the third. And so that is 2 plus 40 plus 600 plus 8,000. And that's how you form this number. And that can go as big as you like or as small as you like as you go the other direction. Okay? So that's how we make our decimal numbers. This is decimal. Meaning 10. Deci is 10. Okay, so what about binary? Well, first of all, why do we need binary? Well, computers, deal with switching, right? Here's a switch. And a switch has two states. Has an on state and an off state. And typically a 0 is associated with off, 1 is associated with on. And computers are just series of switches that are all connected together. You can make logic with switches and so on and so forth, and then you can do mathematics with switches. So it's the same idea. So bi is 2, deci is 10, but bi is 2, meaning two states, 0 and 1. So again, these categories, these different binary digits or bits, right? Bits are binary digits. Mean 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and so on, which is 2, 4, that's 1, 2, 4, 8, 16, 32, so on. So if I have a binary number that is 1, 0, 1, 1, 0, 0, 1, this is 1 times 2 to the 0 plus 0 times 2 to the first plus 0 times 2 to the second plus 1 times 2 to the third plus 1 times 2 to the fourth plus 0 times 2 to the fifth plus 1 times 2 to the sixth. Okay? So that is 1 plus 0 plus 0 plus 8 plus 16 plus 0 plus 64. Okay? So 64 plus 16 is 80 plus 88, 89. So this number is decimal equivalent of 89. This binary number right here. So you can go back and forth. You can go between binary and decimal. You can go between decimal and binary. You can go between other decimal number systems as well. Trinary, quaternary, whatever you want, depending on the situation. I believe because we have 5 or 10 fingers, that's why we ended up with a decimal counting system. Computers only have 2 states, so you only need 2. There's other situations you could end up using. All right. So here's where we kind of bring this together. If we want to make a bit sequence, okay, so let's take this situation. We have this sequence that is going to be 10 bits long. So we have a 10-bit sequence. I know I'm chopping it up too big. Let's see. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, there's a 10-bit sequence. This buffer holds, this buffer, we'll call this a buffer, holds 10 sequences. So this is position, for 2 to the 0 all the way to 2 to the 9th. Okay? And let's think of this buffer that every time, remember now, here's our map. This is our Poincare surface. We have a generating partition that's right like this. Remember, it's 0, 1. So every time I just run this thing and start generating bits, every time it crosses the Poincare surface, it generates a 1 or a 0 every time. And so I just start to put those bits in here, storing them in here, and after I get 10 of them, I'll pop the last one out, right? So B10 will just pop out. And this is B0 going in. And that's how we generate these sequences. Because here's what we want to do. What we want to find is the position in VC and VE. That's how I did it. In VC and VE. So what point, let's just say we have this VC, VE pair, and that is going to generate some bit sequence. And that's what I call this is capital B, will be this 10-bit sequence. Each one of these points in on this map, if you start it there and generate it there, then it will produce a bit sequence. And this will be powerful for us later, because just I want you thinking about this. If you are able to control it so that it goes through the exact point you want it to, remember we did that with controlling with small perturbations. If we control it to go through the exact point we want, then we can generate the bit sequence that we want. So therefore, you could control certain bit sequences and make certain bit sequences happen. And, you can think about it right off the bat that you could communicate that way, because bit sequences relate to information, just like in our computers, And if you can control what it's doing, then you can make it do or say what you want. And you could communicate and all that. There's an interesting paper I think I've put in a list that I want you to read. It's called Communicating with Chaos. Oh my God, I can't spell. Communicating with Chaos by Hayes. Look it up in Physical Review Letters. Take a look at that. You'll see what I'm talking about. Now, so you generate these bits and you can control them. So let's take a look a little bit better. Here's the sequences that are generated when here's the VC position right here on this side, and this is the bit sequence between 0 and I guess 1024, because 2 to the 10 is equal to 1024. So the points that you see here that are in blue, if you land there and you make that your initial condition, then you'll generate that sequence. And I'll prove it to you in a second, and I'm going to give you some code that you can play with it yourself. Okay, so if we go back to this point, so what I did was I ran this, I looked at it, and I found out what bit sequence was generated from a particular point. So this point of 10.334 and minus 0.02318 in VE, VC is 10.334. And remember that we had a constant I sub L, and because that's where the Poincare surface is. And I'll show you what we did. So here's the start right there. That's where I started with these values, right on the Poincare surface, and with the points that would tell me that it would generate that bit sequence. So what happens is it goes through, you can almost trace this and see where it goes. It comes back through. And so the first part of it, as a matter of fact, as you can see, this is kind of where the dividing line is right around here. So those three values out here are the ones. So 1 is over here and 0 is over here. And these ones here, here, and here are generated after it goes out, probably comes back in, as you can see. So you can, here's the example of it right here. So started out, and it doesn't have the actual initial condition because it does the next one after it. So as you can see, here's the sequence that's generated, the same, starting with the smallest value, so here's the 0 crossing, then another 0, then 1. As you can see this, because remember 10.4 is our dividing line, remember? So that's less than 10.4, less than 10.4 here, greater than 10.4, less than, less than, less than, so 0, 0, 0, greater than, less than, greater than, less than. So that initial condition that we started with, which is 10.1 Well, I sub L is the first value, and I'm just going to guess, but I remember it was something like minus 0.0015, I believe. Then 10.3447, and then 0.2318 are negative. Those are the 3 points. That's I sub L, that's V sub C, and that's V sub E. These are the initial conditions that will generate this sequence every time. And then after that, it'll continue on, but I know I'll get that 10-bit sequence. And I was able to do that by running it and storing the values that are generated as a result. And this again, so you can see these, this is your dividing line. Again, here's the 1, here's 0. Here's all your 0 points right here. And here's all your 1 points right there. And they're generated in the right order. So, as we talk next time, we're going to try to put this together with control and show how you can control the chaotic process to generate the bit sequences that you want, encode actual information. That's what we'll talk about next. How do we take actual, real information? I'm gonna do it with images because I want to try to go into that image processing idea. But I'm gonna take an image, I'll break it down into a digital sequence, then show you that you could control that digital sequence no matter how long it is, and it could be millions of points. Control it and embed that actual digital sequence into the chaos, and then communicate that over some sort of channel and whatever, right? Pretty interesting stuff. And I know we're talking a lot of different things. Be sure to ask a lot of questions. But I just wanted to give you a flavor that you could dive in and do some more investigation on your own and see what it's all about. Now I'm going to share with you the MATLAB code that did all of this, and you can play with it yourself and see exactly what's going on. Okay? All right. See you next time.